if we get stuck for a long time, maybe you guys can help us. So we have a triangle ABC. E and F are on AB and AC such that BF is equal to CE. Okay, we've seen this idea before, right? So that just means if we take the midpoint of arc BAC, then it means that basically we have a cyclic quadrilateral through DA and those 2 points, right? So let's call this F.
Actually, it's BF equals CE, not BE equals CF.
BF equals CE. Like this?
I mean, E lies on AB and F lies on AC.
Oh, okay. Like, so B, okay. So it's not like this, right? So are you saying it's like, it's more like this? So, wait, so I'm sorry, is it, so F lies on AB, or F lies on
yeah, F lies on AC.
Oh, okay, you're right. So B, sorry, I got too excited. So BF is equal to CE. I don't know if I've seen a problem like this before. It's interesting. Let me move the diagram around to make it better.
You move point F out of segment AC, because I think that is how the original problem stated.
Oh, F is past C, point C.
Yeah. That's how the original problem was.
All right. Sorry. So I have this ray. Okay. Okay, so I'm going to draw those 2 rays. So this is BF. Oops. And that would be CE. Wait till this goes away. Okay. Even still, it's a little, the diagram's a little messy. Let's see if we can make this better. Okay, so BF is equal to CE. M is the, okay, so we draw the midpoint of BE, CF. So that's M, and then this is N. D is the intersection of BF and CE. So this point right here is D. I and J are the circumcenters of DBE and DCF. So this is I, and this is J. So first we want to show MN is parallel to IJ. That's part A. That's kind of interesting. One sec, guys, I'll be right back. But it looks like GI and M are collinear and GJ and N are collinear. So if we could show that, it's interesting. All right, one sec. All right. Sorry about that.
G is the center of spiral similarity, sending EB to CS. So
Okay.
and they are congruent. No.
So okay, it's the center of the spiral similarity taking BF to CE. So basically triangle EBC is congruent to BGF.
Yes, EGC is congruent to BGS.
Okay. So yeah, so those are both isosceles then.
So GI-M are collinear.
So GI and M are collinear and GJ and N are collinear. All right. And also from there it's kind of obvious, or I think it's obvious by some. Is it obvious by just similarity that IJ would be parallel to MN? Because we want to show GI over GM is GJ over GN. But yeah, those two triangles are similar. So yeah. So part A follows from that, right? Okay. So we've solved part A. Now for part B, let K be the midpoint of MN. And H is the orthocenter of AEF. Prove that HK passes through a fixed point.
This is obvious because G is the antipode of AMN.
G is the antipode of, you say?
Sorry, antipode of A in AMN circumscript.
So
you should move F. Can you move F?
Yeah.
Well, G is not fixed. Is it the midpoint of the altitude? Can you check?
Is the midpoint of the altitude from?
Altitude from A to BC.
Okay. So let's see. We want to see if that's the midpoint. No, it's not. So yeah, it's kind of hard to see. Maybe I can draw like.
Orthocenter of AMN lies on this line.
The orthocenter of AMN. Oh, because I'm changing A.
Not A, F.
F, my bad. Okay.
Maybe it's on A altitude, but at different points.
So sorry, Geo King, did you say the orthocenter of AMN is the point?
The orthocenter of AMN lies on this line because of antipode and midpoint.
Okay. So yeah, it looks like it lies, it looks like it's some point on the altitude. I'm kind of cheating here, but yeah.
Is it orthocenter?
But let's, sorry, I kind of missed the chat a little bit, but hold on one second. Yeah, I think, oh, no, okay, so HK passes through that point, but that's not the fixed point that we're looking for.
Fixed point is the orthocenter of ABC.
Okay, it's the orthocenter of ABC.
I guess. Not sure, but
Okay. Yeah, it looks like it. Because yeah, if we move this around, yeah, it looks like it's the orthocenter of ABC. All right.
L may be useful, so
Yeah,
So is it like Steiner line?
the Steiner line.
Yes.
I don't know too much about the Steiner line. So what is what is the Steiner line?
In a complete quadrilateral, the orthocenters found by the four triangles are collinear.
Okay. So is the quadrilateral ABBC that we want to find the Steiner line of?
yeah, this is just Steiner line. He's right.
Ah.
Because
So
MNN are midpoints, so ABC, AMN, and AEF have the same Mikhail point, so the same Steiner line.
Yes, yes, yes.
okay. So basically it's like, since G is the Mikhail point, we know that these are all cyclic, right? Sorry, I probably don't need to draw all those. I'm gonna erase it. Okay, so let's see. Just opening up that article. So this is a paper, Steiner's theorem. So okay, so there's a bunch of orthocenters that are collinear, is what you're saying. Okay, so we have the orthocenters of ABC. All right, let's see. So we have the orthocenter of ABC. What are the other things that, what are the other, so AMN, right? ABC, AMN, and then AEF. And is G isn't an orthocenter, is it? But K, okay, so the theorem, does it say that these three, the orthocenters of these three are collinear, or? guess I'm trying to see Steiner line of EBCF. Okay. Let me read through this theorem one more time. Sorry. So I guess this is the orthocenters lie on the same line. Okay, so this is the Mikkel point. It's the first one. The centers of the four circles lie on the same circle. The perpendiculars from F. Okay, so it's like property 3. What are the four? So it's taken 3 by 3. Okay, so basically, this is saying if we, okay, if we take BCEF, so yeah, we would have ABC as one of them. So, okay, so if you look at BCEF, so if you take, so ABC would be one of those triangles, AEF would be another one. Okay, so Serdar just posted a link for the previous problem. And then okay, so this is using a lot of stuff from that article. All right. But is G an orthocenter, or like I'm not sure which lemma we use from that. One sec, guys, I'll be right back. Sorry. All right, sorry I was away again, but thanks for waiting. Okay, so there's a lot of different sources related to that last problem. So here's one of them. Serdar posted. Okay. Oh, and this uses a Poncelet point, I think, that, or actually I'm not sure if it does. Okay. There's so many different things. You're speaking of the Mannheim's line. Interesting. Yeah, the main reason I'm pulling this up is just, yeah, if we rewatch the video, then we could just more easily see where it came from. Okay, so this is the lemma that you guys are talking about. It's the anti-Steiner point of the Euler line. All right, so I'm going to go back. Okay, so first I'm just going to type up part A. So a spiral similarity takes GEC to GMN. And so BF equals CE means that those are congruent. So, oh no, I'm sorry, BEC. Yeah, BF, no, GBF. So BF equals CE means that GEC is congruent to triangle GBF. So GBE and GCF are isosceles. So GI and M and G we'll say isosceles and similar. So GI and M are collinear, as are G, J, and M. And then GI over IM equals GJ over JN by the similarity. GI over IM equals GJ over JN. And that means that MN is parallel to IJ. And then I'll say let O be or I'll give it another name. I'll call it P. Let P be the orthocenter of ABC. So G, G is the McKell point of BEFC. And let H be the orthocenter of AMN. So, oh no, it's H is the orthocenter of AEF. No, L, but L will be the orthocenter of AMN. Oh, sorry. One of you are on GEO King, you're on speaker. I'm gonna put you on mute for just a second. Sorry. I'm trying to put, there we go. So is it obvious? So we're saying the McKell point, the midpoint of MN, and the orthocenters are collinear. Is that just a well-known fact from that paper? So I guess we don't really need L, right?
No, actually, L is useful, I guess.
L is useful.
If we prove that H is on LKG, then we are done.
Okay, if you prove that H is on LKG. You guys sound so smart that like when you start saying all these things, like, yeah, I just assume the whole problem's solved. But yeah, I guess it's not that easy. There's still like one more step. All right. L, so we want to show L, G, and K are collinear. This almost looks like a parallelogram. L, M, G, N.
Maybe we shouldn't use L, I guess. It will be problem harder. It will make the problem harder, I guess.
Okay. Let me just check if this is a parallelogram. It almost looks like it.
It's obviously a parallelogram. It's well known that reflection of orthocenter with respect to midpoint is on the circle.
Oh, okay. So
if we delete L, then we can delete M and N.
okay.
Actually, we cannot.
No, because you need K. Yeah. Okay, so you're saying it, but you're saying it's enough to show that H, K, and G are collinear, right?
Yeah.
Because we know that P, K, and G are collinear.
No, because we know that L is on KG and Steiner line is the same. So P is on that line.
Okay.
What if we introduce the circles with diameter BF and CE?
Okay, I can try that. EF and CE. So, oops, want to select L. Whoops. Those two circles?
Yeah, yes. So we just need to show that these 4 points lie on the same radical axis of these two circles.
Okay.
So
But the radical axis of those circles doesn't look like G's on them, right?
Why? Can you try that?
Draw the radical axis, or
Yeah.
oh, it looks like it passes. Oh, I was looking at these circles. No, you're right. I'm sorry. It's my bad. So yeah, they do lie on the radical axis. So we have to prove that. That's part of that theorem about the Steiner line, right? That these points would lie on those circles with those diameters.
So proving
Yes.
K is on the radical axis enough, right?
I think so.
Because we know that orthocenters are on that radical axis.
Okay. So we know that P would lie on it. Is that just part of the theorem? Because P is the orthocenter of AMN, right?
Yeah, we know that orthocenters of ABC, AMN, and AEF are collinear.
Okay.
But we want to see that if K is on that.
Okay. How do we know that G is on it? Is that just part of
We
the
don't need
theorem?
G actually. Is not given in the problem. So
Oh, so we don't even need to know that
so
G is on it, really.
K is the midpoint. K is the midpoint of OL, and since MOLN is a parallelogram, so K also lies on this line.
Okay, so because MO and L is a parallelogram, and
So
so
K lies on this line. K is the midpoint of OL because the diameters are equal according to the problem condition.
okay. So since K is the midpoint of OL, and the diameters. So since K is the midpoint of OL, how does that show that K lies on that line?
Because MOLN is a parallelogram.
So I understand that. So MOLN is a parallelogram, so K is the midpoint of OL, right? And then how do we use that to show that K lies on, or have you shown that K lies on this line? or not yet? Yeah.
Because then it will lie on the radical axis. Because when the circles are congruent, then the radical axis is the perpendicular bisector of the line joining the centers.
Okay. So
He's right.
yeah, because O and L are the standard, so that means K has the same power because it's just KO squared minus the R squared. Okay. Interesting.
So we are done.
Yes, yes.
Okay. So all right, I'm gonna unhide oh no, they're already there. So P Q, sorry. This looks weird. We don't need P actually. Trying to hide this. It's not working well. This is driving me crazy. This line will not hide. Oops. Okay, finally. All right. Yeah, we don't really need Q and R. I'm just going to leave them there so that, yeah, I can draw the final line. But, okay, so it's well known that H, K, and G are collinear. H, K, and G are collinear. And that's well known since AMGN is cyclic. Oh no, P, K, and G are collinear. Wait. Wait, I'm so confused now. Wait, how did I? P is the orthocenter of ABC. What's the orthocenter of AMN? Did we mention that? Oh, L. No, but I renamed it here. Okay, let me redraw that. So we have that, there we go. So let S be the orthocenter of AMN. So it's well known that S, K, and G are collinear. All right. So and then so the Steiner's theorem says that S, H, and P are collinear. And then we have let O and L be the midpoints. Let L and O be the midpoints of BF and CE. And so first of all, then M, so we have M, MONL is a parallelogram because K is the midpoint of MN, and you can just prove that PH and K lie on the radical axis of O and L. So P H and K. So sorry, I'm forgetting this here. So how did we know that that was a parallelogram? Sorry, I'm forgetting. So K is the midpoint of MN, right? And KO NL, oh, they're both midlines, that's right. So L is the midpoint of BF. How does that? Oh, because M is the midpoint of BC, and okay. So MO is half BD, and okay. Okay, so MO is parallel to BF, and LN is parallel to BC. Okay, so LN is parallel to BC and MO is parallel to BC. So okay, so that means that MONL is a parallelogram. So do we have someone new from Vietnam on the session? I don't think I've seen, I think someone new just hopped on. Ngok Bao, sorry if I pronounced it wrong. I'm sure I did. So O, K, and L are collinear. Sorry. You know what? I'm just going to start typing it up here to make room. So OK and L are collinear, and so we wanted to show so HK. Okay, so KO squared, so the power of K with respect to O is equal to KO squared minus R squared, which is KL squared minus R squared, which is the power of K with respect to L. So basically, K lies on the radical axis of those circles. Sorry. I'm going to move this down for just a sec. So K lies on the radical axis of those. And so by Steiner's theorem, H, K, and H, K, S, and P are collinear. On the radical axis. And so HK passes through P. All right, I'm going to move on to the next problem. I think that covers it for this one. So the next one used the Beaven point. So we have a triangle ABC. So the Beaven point is the reflection of the incenter over the circumcenter. I think there's other ways to define it too. This is O, and then I'm going to reflect it. So I think there's another way to define this point and use, if you draw the X centers of ABC and you like take the perpendiculars to each side. I'm just going to leave it like this for now. So if BE prime is the, so then we draw the circumcircle of, let's rename this BE. And then we draw the circumcircle of BCBE. And yeah, so let's change this around a little bit so that we can see more of the figure. My GeoGebra is just not working well today. Okay, so yeah, it probably looks a little better like this. It's like more of a taller triangle. Okay, so we want to draw the antipode of BE. So let's draw the center of the circle and reflect BE about it. Almost looks like that lies on the end circle, but hold on. So this is BE prime. And we want to show that A BE prime goes through the homothency center between the in-touch and excentral triangle. Okay. So, yeah. Let me draw the excentral triangle. So, draw the perpendiculars. So that's the excentral triangle. Let me shrink the diagram. So these 3 points. And maybe it's worth drawing the X circles too, not just the triangle. All right. Seems like IBE is perpendicular to BC. Oh, IBE prime. It does look like it. So yeah, so that looks true. I'm not sure the proof, but it looks true. Let's call this K. Close that. So worth drawing the X circles. So we know that the EBE is perpendicular to BC. We know that that's perpendicular and this is also perpendicular. So yeah, the in-touch triangle and the excentral triangle are homothetic, as the problem mentions. So yeah, what is the center of homothety?
It lies on line OI.
It lies somewhere on the line OI. So, I mean, that's basically where GH, JF, and EK intersect, right? There's too many lines though, so I'm going to erase them, but just wanted to check. Maybe I'll just draw the point, but hide the lines.
I think we need to prove that BE prime is the mixed linear tangent point.
Sorry, hold on one second. I think I drew two of these. Whoops. Oh no, I and L are over 11. We need to prove that BE is the mixed linear tangency point.
BE prime. Can you just check for me?
Yeah. So that would be the same as saying that.
Actually, it isn't. I think.
Yeah, I don't think it can be, because then I M in that point would be linear, right? But yeah, it's interesting that IBE prime is perpendicular to BC. I would not have expected that. We start by just trying to prove that IBE prime is perpendicular to BC. Maybe it's obvious because basically, I mean, we know that BK is equal to CN. It's sufficient to prove that OD is yeah. So yeah, okay, so it's pretty obvious. So it's kind of obvious that yeah, IBE prime is perpendicular to BC. Okay. So basically, this is kind of an interesting problem because it means, like, basically we can take, well, actually, it's not that good of a criterion. Yeah, this is hard. I don't know. I don't even know where you would start on this. What would that mean if A, B prime went through that point? So yeah, is there something else we can find on the homothency? I wonder if LBE prime, well, yeah, it's not gonna be true.
What if we introduce the foot of K on HJ?
Oh, the foot of a J onto something?
K, foot of K on HJ.
Oh, okay. Oh, maybe that passes. Okay, it doesn't pass through L. And it,
So the foot will be collinear with LA.
okay. So the foot of it will be collinear with LA. All right.
And if we try to show like QI B sub B dash collinear.
QI.
No, I mean like QLB sub B dash might be easier to show collinear.
Okay. So yeah, then we could like remove point L. So, okay. So basically you're saying we don't really need it. We can kind of hide point L for now. And we just want to show that oops. Q, A, Q, and B, E prime are collinear. Like that. Because yeah, there's a lot of facts about, I mean, AQ, there's like a lot of well-known facts about like where that meets the circumcircle of ABC, right? So I think,
Yes.
yeah,
MK meets ABC, like these three line concur.
MK, yeah, like MK meets it on the circumcircle, right? So yeah, this is tricky diagram. Like right at that point right there. So really we want to show like A, R, and B, E are collinear, right? Yeah, that looks a little bit easier. Okay, so we want to show A, R, and B, E are collinear. So yeah, we have to use somewhere that BE, we have to use somewhere that like, that this circle passes through BE. both KQ and AI are perpendicular to HJ. Yeah, we kind of define KQ to be perpendicular to HJ. So, yeah.
Sorry, Michael, can you draw the line AK?
AK.
The whole line, I mean.
Oh, sorry. Is the ray good enough?
Yes.
Okay.
Yeah, maybe it's concurrent.
You want me to draw this point? This point? I don't know if you need both those. Okay, so Hakan is saying maybe we can show KBE prime over IBE prime is equal to KQ over AI. That's not a bad idea. And then that would show that A, Q, and BE prime are collinear, which is what we want. So KBE is the same as NP. So yeah, I also like the idea of showing that AR and BE prime are collinear. My head just hurts at this point. Are RS and BET parallel? It almost looks like it.
Can you call the midpoint of BC?
Midpoint of BC, yes. Sorry. No, I think that's, yeah.
You can hide the line AK. I think it is an hypothesis.
Hide the line AK.
Sorry, can you draw the tangent line from B to C with respect to circumscribble B, B, E, C?
Sorry, B to C?
The tangent line to B and C.
Oh, okay. With respect to this circle right here?
Circumscribble B, B, E, C.
Yeah. Okay.
I think that maybe line A, B, E prime. I'm not sure, but maybe.
Okay. Let me check. So then ABE prime would be a, oh no.
Oh.
Doesn't.
Sorry.
Sorry. But yeah, if that was a symmedian, that would be a big thing. Right, something about Hakon's idea. It's a hard one.
Should we move on to the next one?
I think this is the last one I'd chosen. Let's see. There was, if you want, we could finish up this one, but or we could choose another problem if you want. So there was actually one more problem that Geo King sent me, so I could try that one. Oops, sorry. GeoGebra. Oh no, actually, I think I looked at all the ones that Geo King sent me. So yeah, I don't. We could also just, so here's I3435's book. If you want, we could take problems from here. Let's see. It's a good problem. Are all the problems at the end of the book? I'm not sure. Have you guys seen the Hagge circle before?
I've heard of it, but I have never met one.
Okay. Let's see if we can prove it. Okay, so we have a triangle with an orthocenter. Let P be a point. Okay, so then we reflect those 3 points about the sides. And then that's kind of interesting. Okay, so we start with a triangle and an orthocenter. We draw the circumcircle too. And then we draw the orthocenter. Oh, whoops. And then we let P be any point. And we see where these meet the circumcircle. And then we reflect them over the corresponding sides. So this, and this, and we reflect them. So first of all, I think these three reflections are supposed to lie on a circle passing through H. Let me check that that's true. So yeah, the first part of it says that those 3 points lie on a circle passing through H. And then there's a second part Let's see. Okay. See you later, Con. Thanks for joining us. The second part says that we see where those intersect AH, BH, and CH. Okay, so I think it's just saying we draw AH, BH, and CH. It's saying that these concur. So, which is just the same as saying that wait, for CH. Why doesn't CH pass through anything interesting? No, it's saying that okay, so basically we draw the lines through P. What is this double prime? And X, Y, and Z. Okay, so it's saying a couple things. Wait, so we have CE prime. Then A. No, we have AD prime, CF prime, and BE prime. Wait, I'm confused. Oh well. Well, first, can we show that these lie on a circle? D prime, E prime, F prime, and H. Oops. So yeah, let me hide the extra lines.
AH F prime B is cyclic.
A8 or say that again. What's cyclic?
AH F prime B.
Okay.
Cause of reflection.
Oh yeah, because you're taking AF and B and you're reflecting. Yeah, so that's cyclic.
And similarly, others are also.
Okay. Okay, so those are all cyclic. Maybe it's just like an angle chase from this point. I'm not sure. Though I don't know if it's that easy. I'll type up the problem just for the viewers. meet the I'll just say the circle ABC at D, E, F. Let D prime, E prime, F prime be the reflections, I'll just say over BC, CA, and AB respectively. Prove that H, F prime, E prime, D prime is cyclic. Okay, so, all right, so we have those three cyclic quadrilaterals. Is there anything else we can use? I feel like it feels like it should be an angle chase. So angle F prime H D prime is angle BHD prime minus BHF. Yeah, I think it's probably an angle chase from here, right? So not 100% sure, but I think we can calculate this angle. Let's see. So I wish the text didn't overlap the figure, but okay. So, but how do we find angle D prime, E prime, F prime? That would be so the second part of it says that, so I think AH and sorry, something D is that obvious that D prime E prime F prime equals DEF? Maybe is that obvious? Maybe I'm missing something. No, I don't think that's true. Yeah, that's not true. They're close, but C BH. D prime.
Can you check what is angle? Can you check what is angle DEF?
Angle DEF. Oh, I think I did E. Sorry, I think you're right. Yeah.
Yes.
So, whoops. I was comparing two different angles. Yeah. It's my bad. Yeah, those are the same.
Yes.
How do we know that? Okay, so if the problem is true, then we could prove that, but is it just an angle chase to solve this? Let me see also what the second half of the problem says. So we have let A double prime P. Okay, so it's saying you have to take the intersection point. You have to take, okay. So the second half of the problem says, that like if I take this, this, and this, then it says that AH, BH, and CH meet at those points. That's kind of interesting. So yeah, it's saying AH and B prime P concur on the circle is what it's saying. Don't know if that's obvious. Okay, yeah, I'm gonna hop off now because yeah, we're out of time. So thanks everyone for participating, for everyone watching. Thanks again. So I think I might keep going through problems from I3435's book. We were able to solve all of them today, so maybe they were a little on the easier side, or maybe just having all the past background helped. But I'll see if I can find problems next time that are maybe a little more difficult. So if you'd like to join future sessions, feel free to email me at mgreenb801@gmail.com. It's in the description of my video. We meet on Sundays at 8 a.m. US Central Time. Thanks again, and have a great rest of your day.